Hello and welcome. We will continue our basic probability lecture from conditional probability, which is a very important concept in probability theory. Suppose we have two events A and B such that the probability of A is greater than 0, that is, it is not an impossible event, then the conditional probability of B given A can be written as the probability of both A and B occurring divided by the probability of A. Here we want to find the probability that B will occur given that A has already occurred. Since A is known to have occurred, it becomes the new sample space, replacing the original sample space S, and we get to this definition. We can also rewrite this as probability of A and B is equal to the product of the probability of A and the probability of B given A. Let's look at an example. A single die is tossed once. We want to estimate the probability that a number less than 4 will turn up. Now there are two parts of this example. In the first part, we are given no additional information, whereas in the second part, we are given that the toss resulted in an odd number. Let's first solve part A. We know the sample space consists of numbers from 1 to 6. B is the event we are interested in, that is a number less than 4 will turn up. Then we know from the theorems we discussed in part 1 of this video is that B can be written as union of simple events 1, 2 and 3. The probability of B is therefore equal to H divided by N. In this case, H is 3 and N is 6. So the probability of B is equal to 1 by 2. Now to part B, we are given that the toss resulted in an odd number, so we have an additional information. We call this event A, which comprises of 1, 3, 5 that are odd numbers, and it is the new sample space. And using the above methodology, we can see that probability of A is 1 by 2. Then the probability of A and B can also be calculated to be 1 by 3. And if we plug these into conditional probability equation, we see that the probability of B given A is equal to 2 by 3. Okay, more theorems on conditional probability. Theorem 9 states that the probability that events A sub 1, A sub 2 and A sub 3 all occur is equal to the probability that A sub 1 occurs times the probability that A sub 2 occurs given that A sub 1 has already occurred times the probability that A sub 3 occurs given that both A sub 1 and A sub 2 have occurred. Theorem 10 states that if an event must result in one of the mutually exclusive events A sub 1 to A sub n, then probability of A is equal to the sum of the product of the probability of A sub 1 times the probability of A given A sub 1 has occurred. Independent events are events which are not affected by the occurrence of other events. For example, if we roll a die twice, then the outcome of the first roll and the second roll have no effect on each other. It means they are independent. On the other hand, when you choose a ball from a bag and do not replace it, you are changing the number of balls in the bag, and therefore the outcome of choosing the first ball will have an effect on the outcome of choosing the second ball. For example, if you choose a green ball the first time, the probability of choosing a green ball the second time will decrease. Therefore, these are dependent events. We say that two events A and B are independent if probability of B given A is equal to the probability of B. This is equivalent to saying that probability of both A and B occurring is equal to the product of the probability of A and the probability of B. Similarly, three events A sub 1, A sub 2 and A sub 3 are independent if they are pairwise independent and the probability of all three events occurring is equal to the product of the probabilities of A sub 1, A sub 2, and A sub 3. Now we have another important topic, which is Bayes' theorem. It is important because it provides a mathematical framework for updating probabilities of hypotheses based on new evidence, which enables more informed decisions and predictions in various fields, especially when dealing with uncertainty. We can use the commutative property of set intersection and derive the expression which is known as the Bayes rule or Bayes theorem. We can use theorem X to write this expression, which allows us to find the probabilities of various events A sub 1 up to A sub n that can cause A to occur. Bayes' theorem provides us with a general recipe to estimate the value of the parameter theta, given that we have observed some data y. On the right-hand side in the numerator, we have the product of the likelihood function and the prior. The likelihood function links the observed data with the unknown parameters. The prior distribution represents the uncertainty about the parameters before observing the data y. In the denominator, we have the normalization constant or marginal likelihood or the evidence term, which represents the global information of the posterior distribution at a specific point in relation to the surrounding points. The term on the left-hand side is called the posterior, which is our updated belief in the parameter theta after we take into account evidence y. When sample size is very large, direct counting of sample points becomes impossible. In such cases, combinatorial analysis can be useful. Let's look at the fundamental principle of counting, which states that if one thing can be accomplished in n sub 1 different ways, and after this a second thing can be accomplished in n sub 2 different ways, and finally a kth thing can be accomplished in n sub k different ways, then all k things can be accomplished in the specified order in n sub 1 times n sub 2 times and up to n sub k different ways. Let's look at an example in which we want to find the number of ways of choosing a shirt and a tie if someone has 2 shirts and 4 ties. Using the fundamental principle of counting, we can see there are 2 ways of choosing a shirt, and after this there are 4 ways of choosing a tie. So the person has 2 times 4, which equals 8 number of ways of choosing a shirt and a tie. Now we will review permutations and combinations, which are methods for selecting elements from a set, but they differ in order and arrangement. A permutation is an arrangement of items where order is important. If the order of selection changes, it counts as a different arrangement. Suppose we are giving n distinct objects and we want to arrange R of these objects. There are n different ways of selecting the first object, n minus 1 different ways of selecting the second object, and n minus r plus 1 different ways of selecting the rth object. Then using the fundamental principle of counting, we can write the different arrangements or permutations as this expression. Here, NPR, which is read as the n permutation R, and it represents the number of permutations of n objects taken R at a time, and it is equal to n factorial divided by n minus R factorial. Let's look at an example. In this, if we have 5 books and we want to find the number of ways to arrange 3 of them on a shelf, and remember, in this case order matters, ABC is not equal to BAC. Then we can use the above formula and we can see that there are 60 ways of arranging 3 books on a shelf if we have 5 books. Now suppose that a set consists of n objects of which n sub 1 are of one type, n sub 2 are of second type, and n sub k are of kth type. Here n is equal to the sum of n sub 1, n sub 2, and up to n sub k. Then the number of different permutations of the objects is given by this expression. Let's look at an example. In this example, we want to find the number of different permutations of the 11 letters of the word Mississippi, which contains 1M, 4S, 4 I's, and 2 P's. Plugging this into the above formula, we find that there are 34,650 different permutations or arrangements of the letters in word Mississippi. In permutations, we saw that we are interested in the order of arrangement of the objects. However, in many problems, we are only interested in choosing objects without regard to order. A combination is a selection of items where order does not matter. That is, ABC is the same as BAC. Here we can use this formula, which represents the combination of n things taken R at a time. Let's look at an example in which we want to find the number of ways in which 3 cards can be selected from a total of 8 different cards. Plugging these into the above formula, we can see that there are 56 ways 3 cards can be chosen from a total of 8 different cards. With this, we conclude this video. I hope you liked it. Don't forget to subscribe, share, and like this video. Thanks for watching, and see you all in the next video in which we will solve some example problems. Thank you.